right, well, we looked at inertial reference frames. We talked about this idea of, well, if I'm observing a moving inertial reference frame, the motion of the object is different in terms of its path and its velocity because of the way that I'm observing. So we have to make sure we're always kind of thinking about the observer's reference frame and the object's reference frame. So we're going to look at that a little bit more mathematically. These are called Galilean transformations of speed, and we're going to do an example. It's posted up above to kind of elucidate this idea a little bit more. So a man is on a train and he's moving at 4 meters per second. And he can throw a ball at the speed of 7 meters per second. Okay, so he's moving at 4 meters per second. He can throw a ball at 7 meters per second. If I'm an observer on the ground, so relative to the ground, what is the ball's speed doing? And we talked about this in sort of general terms in the Introduction to Inertial Reference Frames mini lecture. Now we're going to put it into mathematical terms. So we need to define a few things. We want to define the speed of the reference frame that the object is moving in. And then we want to define the reference frame of the observer, okay, and what the velocity of the object is to the observer. And then, of course, we have the velocity of the motion itself of that reference frame. So if we're going to think about this as moving on a horizontal axis, okay, so the horizontal reference frame, okay, so moving on the horizontal axis, the speed that he can throw that ball is 7 meters per second. The speed of the reference frame is 4 meters per second. Okay? And if we want to know what is the observed speed, we'll just call that use of x for the observed reference frame. That's what we're interested in knowing. Well, in general, the observed reference frame is equal to the velocity in the reference frame of the object plus the velocity of the reference frame itself, okay? So, if the object and the reference frame are moving in the same direction, these are both going to be the same sign. They're both going to be positive in this case. So if the velocity of the object is moving at 4 meters per second, the velocity of the reference frame, and the velocity of the object in that reference frame is 7 meters per second, and they're in the same direction, then if the man throws the ball in the same direction that the train is moving, then as the observer on the ground, it's moving faster at 11 meters per second. And that makes some sense, right? I not only see that ball moving at 4 meters per second as it goes by me, but now I throw it 7 meters per second, and I observe that ball at 11 meters per second. Well, the same relationship is true in part B, but in part B, they're moving in opposite directions. So my use of x, so this is part 1, 2, part B, or 2, my transformed velocity, my relative velocity, is now going to be minus 7 meters per second because it is opposite meters per second of the motion of the reference frame, so the motion of the train. And so I observe the motion of the ball at minus 3 meters per second. Okay? But now what about part 3, where I am throwing the ball perpendicular? In the case where I'm throwing the ball perpendicular, the ball has a component of its motion in the horizontal direction, and now it also has a component of that motion perpendicular to that direction. That's what's at 7. So overall, as the relationship of the observer, it has a component of the moving reference frame plus now a component in a new reference frame. We're going to call that u sub y because it's perpendicular, so I'm just going to use the y direction. And we know that to get the magnitude then of the velocity as observed, I'm going to take the Pythagorean theorem for those two components. And when we do that, we get the square root 7 squared plus 4 squared, and that gives us 8 meters per second. So relative to the observer watching the ball being thrown in the perpendicular direction while on the train, it now has a component in the direction of the motion of the train. Should have flipped those two around. I'm sorry, that's misleading. I just used the numbers, but I didn't pay attention to make sure they're consistent. It should be 4 squared plus 7 squared. So it has that in the direction of the train at that speed plus the direction perpendicular. So we take Pythagorean theorem and get our 8 meters per second. So these transformations, looking at what is the observed velocities or velocity transformations, the observed velocity is the observed velocity is the reference frame, the object within the reference frame, and the motion of the reference frame. All right, good job.